Hello, welcome to the video lecture series on digital image processing. In our last lecture, we have started discussion on the Fourier transformation, and towards the end we have seen some of the properties of the Fourier transformation. So, what we have done in the last class is we have talked about the Fourier transformation both in the continuous and in the discrete domain, and we have talked about some of the properties of the Fourier transformation like the separability property and the translation property. Today, we will continue with our lecture on the Fourier transformation, and we will see the other properties of the Fourier transformation, and we will talk about how to implement Fourier transformation in a faster way, that is, we will talk about the first Fourier transformation algorithm. So, in today's lecture, we will see the properties of the discrete Fourier transformation, specifically the periodicity and conjugate property of the Fourier transformation. We will talk about the rotation property of the Fourier transformation. We will see the distributivity and the scaling property of the Fourier transformation, followed by the convolution and correlation property of the Fourier transformation. And then we will talk about an implementation, a first implementation of the Fourier transformation, which is called first Fourier transform. So, first let us see what just try to repeat what we have done in the last class. So, in the last class, we have talked about the separability. We have talked about the separability of the Fourier transformation. And here we have seen that given a two-dimensional signal f x y in the discrete domain, that is samples of this two-dimensional signal f x y, we can compute the Fourier transformation of f x y as f u v, which is given by the expression 1 upon capital N, where our original signal f x y is of dimension capital N by capital N. And the Fourier transformation expression comes as f x y into e to the power minus j 2 pi by n into u x plus v y, where both x and y vary from 0 to capital N minus 1. And if I rearrange this particular expression, then this expression can be written in the form 1 upon capital N, then summation e to the power minus j 2 pi by capital N u x, and then multiply this quantity by capital N, and then 1 upon n, again a summation f x y e to the power minus j 2 pi by capital N v y. So, in the inner summation, it is taken from y equal to 0 to capital N minus 1, and the outer summation is taken from x equal to zero to capital N minus 1. And here we have seen that this inner summation, this gives the Fourier transformation of different rows of the input image f x y, and the outer summation, this outer summation gives the Fourier transformation of different columns of the intermediate result that we have obtained. So, the advantage of this separability property that we have seen in the last class is because of this separability property, we can do the Fourier transformation, two-dimensional Fourier transformation in two steps. In the first step, we take the Fourier transformation of every individual row of the input image array, and in the second step, we can take the Fourier transformation of every column of the intermediate result that has been obtained in the first step. So, now the implementation of the two-dimensional Fourier transformation becomes very easy. So, the scheme that we have said in the last class is like this. If I have an input array given by f x y, this is the x dimension, this is the y dimension. So, first what we do is we do row transformation, that is take Fourier transformation of every row of the input image, multiply the result by capital N. So, what I get is an intermediate result array, and this intermediate result array gives Fourier transformation of different rows of the input image. So, this is represented as f x v, and this is my x dimension, and this becomes the v dimension. And after getting this intermediate result, I take the second step of the Fourier transformation, and now the Fourier transformation is taken for every columns. So, I do column transformation, and that gives us the final result of the two-dimensional Fourier transformation f u v. So, this becomes my u axis, the frequency axis u, this becomes the frequency axis v, and of course, this is the origin 0 0. So, it shows that because of the separability property, now the implementation of the two-dimensional Fourier transformation has been simplified, but because the two-dimensional Fourier transformation can now be implemented as two step of one-dimensional Fourier transformation operations, and that is how we get this final Fourier transformation f u v in the form of the sequence of one-dimensional Fourier transformations. And we have seen in the last class that the same is also true for inverse Fourier transformation. Inverse Fourier transformation is also separable. So, given an array f u v, we can do first inverse Fourier transformation of every row, followed by inverse Fourier transformation of every column, and that gives us the final output in the form of f x y, which is the image array. So, this is the advantage that we get because of separability property of the Fourier transformation. The second one, the second property that we have discussed in the last class is the translation property. So, this translation property says that if we have an input image f x y, input image array f x y, then translate this input image by x naught y naught. So, what we get is a translated image f x minus x naught and y minus y naught. So, if we take the Fourier transformation of this, we have found that the Fourier transformation of this translated image, which we had represented as f t u v, this became equal to f u v into e to the power minus j 2 pi by capital N u x naught plus v y naught. So, if you find, so in this case the Fourier transformation of the translated image is f u v, that is the Fourier transform of the original image f x y, which is multiplied by e to the power minus j 2 pi by n u x naught plus v y naught. So, if we consider the Fourier spectrum of this particular signal, you will find that the Fourier spectrum, that is F transpose F T U V, will be same as F U V. Now, this term e to the power minus j 2 pi by n u x naught plus v y naught, this simply introduces an additional phase shift, but the Fourier spectrum remains unchanged. And in the same manner, if the Fourier spectrum f u v is translated by u naught v naught, so instead of taking f u v, we take f u minus u naught, v minus v naught, which obviously is the translated version of f u v, where f u v has been translated by vector u naught v naught in the frequency domain. And if I take the inverse Fourier transform of this, the inverse Fourier transform will be f x y into e to the power j 2 pi by n into u naught x plus v naught y. So, this also can be derived in the same manner in which we have done the forward Fourier transformation. So, here you find that if f x y is multiplied by this exponential term e to the power j 2 pi by n u naught x plus v naught y, then the corresponding in the frequency domain, its Fourier transform is simply translated by the vector u naught v naught. So, what we get is f u minus u naught and v minus v naught. So, under this translation property, now the DFT pair becomes, if we have f x y e to the power j 2 pi by capital N u naught x plus v naught y, the corresponding Fourier transformation of this is f u minus u naught, v minus v naught, and if we have the translated image f x minus x naught, y minus y naught, the corresponding Fourier transformation will be f u v e to the power minus j 2 pi by n u x naught plus v y naught. So, these are the Fourier transform pairs under translation. So, this f x y and f x minus x naught, y minus y naught. So, these two expressions gives you the Fourier transform pairs, the DFT pairs under translation. So, these are the two properties that we have discussed in the last lecture. Today, let us talk about some other properties. So, the third property that we will talk about today is the periodicity and conjugate property. So, the first one that we will discuss is the periodicity and the conjugate property. The periodicity property says that both the discrete Fourier transform and the inverse discrete Fourier transform, that is DFT and IDFT, are periodic with a period capital N. So, let us see how this periodicity can be proved. So, this periodicity property says that f u v, this is the Fourier transform of our signal f x y, this is equal to f u plus n v, which is same as f u v plus n, which is same as f u plus capital N v plus capital N. So, this is what is meant by periodic. So, if you find that the Fourier transformation f u v is periodic both in x direction and in y direction, that gives rise to f u v is equal to f u plus n f v plus n, which is same as f u plus n v and which is also same as f u v plus n. Now, let us see how we can derive or we can prove this particular property. So, you have seen the Fourier transformation expression, as we have discussed many times, f u v is equal to double summation f x y e to the power minus j 2 pi by capital N u x plus v y. Of course, we have to have the scaling factor 1 upon capital N, where both x and y vary from 0 to capital N minus 1. Now, if we try to compute f u plus capital N v plus capital N, then what do we get? Following the same expression, this will be nothing but 1 upon capital N, then double summation f x y e to the power minus j 2 pi upon capital N, and now we will have u x plus v y plus capital N x, because now u is replaced by u plus capital N. So, we will have capital N x plus capital N y, where both x and y will vary from 0 to capital N minus 1. Now, the same expression, if we take out this capital N x and capital N y in a separate exponential, then this will take the form 1 upon capital N double summation f x y e to the power minus j 2 pi upon capital N u x plus v y into e to the power minus j 2 pi into x plus y. Now, if you look at this second exponential term, that is e to the power minus j 2 pi x plus y, you find that x and y are the integer values. So, x plus y will always be integer. So, this will be the exponential e to the power minus j some k times 2 pi. Okay. And because this is an exponentiation of some integer multiple of 2 pi, so the value of this second exponential will always be equal to 1. So, finally, what we get is 1 upon capital N double summation f x y into e to the power minus j 2 pi upon capital N into u x plus v y. And you find that this is exactly the expression of f, u and v. So, as we said that the discrete Fourier transformation is periodic with period n, capital N, both in the u direction as well as in the v direction, and that is that can very easily be proved like this. By this mathematical derivation, we have found that f u plus capital N v plus capital N is same as f u v, and the same is true in case of inverse Fourier transformation. So, if we derive the inverse Fourier transformation, then we will get the similar result, showing that the inverse Fourier transformation is also periodic with period capital N. Now, the other property that we said is the conjugate property. The conjugate property says that if f x y, this function, if this is a real valued function, f x y, if it is a real valued function, in that case the Fourier transformation f u v will be f star minus u minus v, where this f star indicates that it is complex conjugate. and obviously because of this, if I take the Fourier spectrum, f u v will be same as f of minus u minus v. So, this is what is known as the conjugate property of the discrete Fourier transformation. Now, find that using the periodicity property helps to visualize the Fourier spectrum of a given signal. So, let us see how this periodicity property helps us to properly visualize the Fourier spectrum. So, for this we will consider a one dimensional signal. Obviously, this can very easily be extended to a two dimensional signal. So, by this what we mean is, if we have a one dimensional signal say f x, whose Fourier transform is given by capital F u, then as we said that the periodicity property says that f u is equal to f of u plus capital N, and also the Fourier spectrum f of u is same as f of minus u. So, this says that f u has a period of length capital N, and because the spectrum f u is same as f of minus u. So, the magnitude of the Fourier spectrum of the Fourier transform is centered at the origin. So, by this what we mean is, let us consider a figure like this. You find that this is a typical Fourier transform of a particular signal, and here you find that this Fourier spectrum, the Fourier transform is centered at the origin, and if you look at the frequency axis, so this is the u axis. If you look at this frequency axis, you will find that f of minus u, the magnitude of f of minus u is same as the magnitude of the f of plus u. So, this figure shows that the transform values, if we look at the transform values from n by 2 plus 1. So, that is somewhere here, this is n by 2 plus 1 to n minus 1. So, that is somewhere here. So, find that the transform values in the range n by 2 plus 1 to n minus 1, this is nothing but the transform values in the left transform values of the half period in the left half in the left of the origin. So, just by looking at this, the transform values from n plus 1 n by 2 plus 1 to n minus 1, you find that these values are nothing but the reflections of the half period to the left of the origin 0. But what we have done is, we have computed the Fourier transformation in the range 0 to n minus 1. So, we will get all the Fourier coefficients in the range 0 to n minus 1. So, the Fourier coefficients ranging the values of u from 0 to n minus 1. And because of this conjugate property, you will find we find that in this range 0 to capital N minus 1, what we get is 2 back to back half periods of this interval. So, this is nothing but 2 back to back half periods. So, this is one half period, this is one half period, and they are placed back to back. So, to display this Fourier transformation coefficients in the proper manner, what we have to do is, we have to displace the origin by a value capital N by 2. So, by displacement, what we get is this. So, here you find that in this particular case, the origin has been shifted to capital N by 2. So, now what we are doing is, instead of considering the Fourier transformation f u, we are considering the Fourier transformation f u minus capital N by 2, And for this displacement, what we have to do is we have to multiply f x by minus 1 to the power x. So, every f x has to be multiplied by minus 1 to the power x, and this result, if you take the DFT of this, then what we get is the Fourier transformation coefficients in this particular form, and this comes from the shifting property of the inverse Fourier transformation. So, this operation we have to do if we want to go for the proper display of the Fourier transformation coefficients. The next property that we will talk about is the rotation property. Rotation property of the discrete Fourier transformation. So, to explain this rotation property, we will introduce the polar coordinate system, that is, we will now replace x by r cosine theta, y will be replaced by r sin theta, okay. U will be replaced by omega cosine phi, and v will be replaced by omega sin phi. So, by this, now our original two-dimensional signal, two-dimensional array in the plane f x y gets transformed into f r theta, and the Fourier transformation f u v, the Fourier transform coefficients f u v now gets transformed into f of omega phi. Now, using these polar coordinates, if we find out, compute the Fourier transformation, then it will be found that f of r theta plus theta naught, the corresponding Fourier transformation will be given by capital F omega phi plus theta naught. So, this will be the Fourier transformation pair in the polar coordinate system. So, this indicates our original signal was f r theta. If I rotate this f r theta by an angle theta naught, then the rotated image becomes f r theta plus theta naught. And if I take the Fourier transform of f r theta plus theta naught, that is the rotated image which is now rotated by an angle theta naught, then the Fourier transform becomes f omega phi plus theta naught, where f omega phi was the Fourier transform of the original image f r theta. So, this simply says that if I rotate image f x y by an angle say theta naught, its Fourier transformation will also be rotated by the same angle theta naught, and that is what is obvious from this particular expression, because f of r theta plus theta naught gives rise to the Fourier transformation f of capital F omega plus omega phi theta phi plus theta naught, where f omega phi was the Fourier transformation of f r theta. So, by rotating an input image by an angle theta naught, the corresponding Fourier transform is also rotated by the same angle theta naught. So, to illustrate this, let us come to this particular figure. So, here you find that we had a rectangle, an image where we have all values equal, we have pixel values equal to 1 within a rectangle, and outside this the pixel values are equal to 0. And the corresponding Fourier transformation is this. So, here the Fourier transformation coefficients or the Fourier spectrum is represented in the form of intensity values in an image. The second pair shows that the same rectangle is now rotated by an angle 45 degree. So, here we have rotated this rectangle by an angle 45 degree, and here you find that if you compare the Fourier transformation of the original rectangle and the Fourier transformation of this rotated rectangle, here also you find that the Fourier transform coefficients, they are also rotated by the same angle of 45 degree. So, this illustrates the rotation property of the discrete Fourier transformation. The next property that we will talk about is what is called distributivity. And scaling property. The distributivity property says that if I take two signals, two arrays f1 xy and f2 xy. So, these are two arrays. Take the summation of these two arrays f1 xy and f2 xy, and then you find out the Fourier transformation of this particular result, that is f1 xy plus f2 xy, and take the Fourier transform of this. Now, this Fourier transformation will be same as the Fourier transformation of f1 xy plus Fourier transformation of f2 xy. So, this is true under addition, that is for these two signals f1 xy and f2 xy. If I take the addition, if I take the summation and then take the Fourier transformation, the Fourier transformation of this will be the summation of the Fourier transformation of individual signals f1 xy and f2 xy. But if I take the multiplication, that is if I take f1 xy into f2 xy and take the Fourier transformation of this product, this in general is not equal to the Fourier transform of f1 xy into the Fourier transform of f2 xy. So, this shows that the discrete Fourier transformation, and same is true for the inverse Fourier transformation. So, this shows that the discrete Fourier transformation and its inverse is distributive over addition, but the discrete Fourier transformation and its inverse is in general not distributive over multiplication. So, the distributivity property is valid for addition of the two signals, but it is not in general valid for multiplication of two signals. So, the next property of the same discrete Fourier transform that we will talk about is the scaling property. The scaling property says that if we have two scalar quantities a and b, now given a signal f x y, multiply this by the scalar quantity a, its corresponding Fourier transformation will be f u v multiplied by the same scalar quantity a, and the inverse is also true. So, if I multiply a signal by a scalar quantity a and take its Fourier transformation, then we will find that Fourier transformation of this multiplied signal is nothing but the Fourier transformation of the original signal multiplied by the same scalar quantity, and the same is true for the reverse, that is also for inverse Fourier transformation. And the second one is, if I take f of a x b y, that is now you scale the individual dimensions, x is scaled by the scalar quantity a, the dimension y is scaled by the scalar quantity b, the corresponding Fourier transformation will be 1 upon a into b, then Fourier transformation u by a and v by b. and this is the reverse. So, these are the scaling properties of the discrete Fourier transformation. Now, we can also compute the average value of the signal f x y. Now, the average value for f x y is given by, if I represent it like this is nothing but 1 upon capital N square into summation of f x y, where the summation has to be taken for x and y varying from 0 to capital N minus 1. So, this is what is the average value of the signal f x y. Now, find that for the Fourier coefficient, the transform coefficient say f 0 0, what is this coefficient? This is nothing but 1 upon capital N, then double summation f x y, because all the exponential terms will lead to a value 1, and this summation has to be taken for x and y varying from 0 to capital N minus 1. So, you find that there is a direct relation between the average of the two dimensional signal f x y and its 0th Fourier coefficient, DFT coefficient. So, this clearly shows that the average value f x y, the average value is nothing but 1 upon capital N into the 0th coefficient, 0th discrete Fourier transformation coefficient, and this is nothing but, because here the frequency u equal to 0, frequency v equal to 0. So, this is nothing but the DC component of the signal. So, the DC component divided by n, that gives you the average value of the particular signal. The next property, this we have already discussed in one of our earlier lectures, when we have discussed about the sampling and quantization, that is the convolution property. In case of convolution property, we have said that if we have say two signals f x, multiply this with the signal g x, then the Fourier transform in the frequency domain, this is equivalent to f of u convolution with g of u. Similarly, if I take the convolution of two signals f x and g x, the corresponding Fourier transformation in the Fourier domain, it will be the multiplication of f u and g u. So, the convolution of two signals in the spatial domain is equivalent to multiplication of the Fourier transformations of the same signals in the frequency domain. On the other hand, multiplication of two signals in the spatial domain is equivalent to convolution of the Fourier transforms of the same signals in the frequency domain. So, this is what is known as the convolution property. The other one is called the correlation property. The correlation property says that if we have two signals say f x y and g x y, so now we are taking two dimensional signals, and if I take the correlation of these two signals f x y and g x y in the frequency domain, this will be equivalent to the multiplication f star u v, where this star indicates the complex conjugate into g u v. And similarly, if I take the multiplication in the spatial domain, that is f star x y into g x y, in the frequency domain, this will be equivalent to f u v correlation with g u v. So, these are the two properties which are known as the convolution property and the correlation property of the Fourier transformations. So, with this we have discussed the various properties of the discrete Fourier transformation. Now, let us see an implementation of the Fourier transformation, because if you look at the expression of Fourier transformation, the expression we have told many times, this is f u v, which is same as f x y e to the power minus j 2 pi by capital N u x plus v y, where both x and y vary from 0 to capital N minus 1, and this divided by 1 upon n. So, if I compute, if I analyze this particular expression, which we have done earlier also in relation with unitary transformation, you will find that this takes n to the power 4 number of computations. In case of one dimensional signal, f u will be given by f x e to the power minus j 2 pi by capital N u x, summation of this over x equal to 0 to capital N minus 1, and you have to scale it by 1 upon n. This particular expression takes n square number of computations. So, obviously, the number of computations, and each of these computations are complex addition and multiplication operations. So, you find that a computational complexity of n square for a data set of size capital N is quite high. So, for implementation, we have discussed earlier that if our transformations are separable, in that case we can go for first implementation of the transformations. Let us see how that first implementation can be done in case of this discrete Fourier transformation. So, because of this separability property, we can implement this discrete Fourier transformation in a faster way. So, for that what I do is, let us represent this particular expression f u is equal to 1 upon capital N f x e to the power minus j 2 pi by n u x, take the summation from x equal to 0 to capital N minus 1. We represent this expression in the form 1 upon capital N f x. Now, I introduce a term w n to the power u x, where x varies from 0 to capital N minus 1. Now, here this w n is nothing but e to the power minus j 2 pi by capital N. So, we have simply introduced this term for simplification of our expressions. Now, if I assume, which generally is the case, that the number of samples n is of the form say 2 to the power n. So, if I assume that number of samples is of this form, then this capital N can be represented as 2 into capital M. And let us see that how this particular assumption helps us. And with this assumption, now we can rewrite f u as 1 upon 2 m, because n is equal to 2 m. So, now I can write 1 upon 2 m, then take the summation f x into w 2 m to the power u x, where x now varies from 0 to 2 m minus 1. The same expression I can rewrite as half 1 upon capital M summation f 2x w 2m to the power u into 2x plus 1 upon capital M summation f 2x plus 1 w 2m to the power u into 2x plus 1. where x varies from 0 to capital M minus 1. Here also x varies from 0 to capital M minus 1. Now, by this you see that what we have done, f2x as x varies from 0 to capital M minus 1, this gives us only the even samples of our input sequence. Similarly, f2x plus 1 as x varies from 0 to capital M minus 1, this gives us only the odd samples of the input sequence. So, we have simply separated out the even samples from the odd samples. And if I further simplify this particular expression, this expression can now be written in the form half into 1 upon capital M summation f2x into w capital M to the power u x, where x varies from 0 to capital M minus 1, plus 1 upon capital M summation f2x plus 1 w m to the power u x into w 2m to the power u. So, after some simplification, the same expression can be written in this particular form. Now, if you analyze this particular expression, you find that the first summation, this one, gives you the Fourier transform of all the even samples. So, this gives you f even u, and this quantity in the second summation, this gives you the Fourier transformation of all the odd samples. So, I write it as odd u, and in this particular case u varies from 0 to capital M minus 1. Okay. So, by separating the even samples and odd samples, I can compute the Fourier transformation of the even samples to give me f even u. I can compute the Fourier transformation of the odd samples to give me f odd u, and then I can combine these two to give me the Fourier DFT coefficients of values from 0 to capital M minus 1. Okay. Now, following some more property, so effectively what we have got is f u is equal to half f even u plus f odd u into w 2m to the power u. Now, we can also show that w m to the power u plus m is same as w m to the power u. This can be derived from the definition of w m, and also we can find out that w 2m u plus m is same as minus w 2m to the power u. So, this tells us that capital F u plus capital M is nothing but half of f even u minus f odd u into w 2m to the power u. So, here again u varies from 0 to m minus 1, that means this gives us the coefficients from m to 2m minus 1. So, I get back all the coefficients. The first part, this part gives us the coefficient from 0 to m minus 1, and this half gives us the coefficients from capital M to 2m minus 1. Now, what is the advantage that we have got? In our original formulation, we have seen that the number of complex multiplications and additions were of the order of n square. Now, we have divided the n number of samples into two halves, For each of them, for each of the hops, when I compute the discrete Fourier transformation, the amount of computation will be n square by 4 for each of the hops, and the total amount of computation will be of order n square by 2, taking 2 hops, considering 2 hops separately. So, straightway we have got a reduction in the computation by a factor of 2. So, it is further possible that this odd half of the samples and the even half of the samples that we have got, we can further subdivide it. So, from n by 2 we can go to n by 4, from n by 4 we can go to n by 8 number of samples, from n by 8 we can go to n by 16 number of samples, and so on until we are left with only 2 samples. So, if I go further breaking this sequence of samples into smaller sizes, compute the DFTs of each of those smaller size samples and then combine them together, then we will find that we can gain enormously in terms of amount of computation. And it can be shown that for this first Fourier transform implementation, the total number of computation is given by n log n, where log is taken with base 2. So, this gives enormous amount of computation as enormous gain in computation as against n square number of computations that is needed for direct implementation of discrete Fourier transformation. So, with this we have come to the end of our discussion on Fourier transformation. Now, let us discuss about the quiz questions that we have given in our last class. The first question, we said that find out DFT coefficients of a digital image fxy of size capital N by capital N, where fxy equal to 1 for all values of x and y. Now, this computation is very simple. Here you find that FUV will be simply summation 1 upon n fxy e to the power minus j 2 pi by capital N ux plus vy. Now, for simplicity, let me break it into 2 summations. So, I will write it as 1 upon capital N into e to the power minus j 2 pi by capital N summation f x y. Now, f x y is equal to 1. So, I can simply forget this term f x y. So, this will be simply e to the power minus j. So, this is u x e to the power minus j 2 pi by n v y. Now, let us take one of these terms. If I expand this, so summation e to the power minus j 2 pi by capital N v y, this will be simply 1 plus e to the power minus j 2 pi by capital N plus e to the power minus j 2 pi by capital N into 2v, this is into v, plus it continues like this, and there will be total capital N number of terms. And if you look at this particular series, it is nothing but a GP series having capital N number of terms. So, this summation will simply be 1 minus e to the power minus j 2 pi into v, okay, divided by 1 minus e to the power minus j 2 pi by capital N into v. And this particular term will be equal to 1 only when v equal to 0, and it will be equal to 0 when v is non-zero. So, by substituting this, and same is the case for the other summation. So, by substituting this result in this expression, what we get is f u v is equal to 1 in this particular expression when u and v is equal to 0, and this is equal to 0 when u and v are non-zero. So, this is the final result that we will get for the first problem. Now, coming to the second problem, consider the sample values of a one-dimensional signal as given below. Find out the DFT coefficients and also show that the inverse DFT produces the original sample values. This is very simple. You simply replace these values in our DFT expressions. So, you get the DFT coefficients f0, f1, f2 and f3, and whatever value you get as the coefficients, you replace those values in our inverse DFT expression, and you will see that you can get back the same sample values. Now, coming to the today's questions. The today's questions are: what is the time complexity of first Fourier transformation? The second question is: show that the discrete Fourier transformation and its inverse are periodic functions. Third question is: find out the Fourier coefficients for the following set of one-dimensional signals using the first Fourier transformation technique, and verify that the result obtained using the first Fourier transformation technique is same as that using direct implementation of discrete Fourier transformation technique. Thank you.